Hi guys, welcome back to the channel. Hope y'all are doing well. Today we're going to design an advertisement clicks aggregator. In this screenshot over here, you can see how a Google ad looks like. Whenever someone clicks on the ad, Google stores that click event into their database in real time. Tracking and aggregating clicks does not only apply to the advertisement industry. Most platforms nowadays, such as YouTube, Instagram, or any other website or app, they always care about tracking or just aggregating clicks happening all over their platform. So the design that we're going to come up with is not only going to apply to tracking advertisement clicks in real time, but also clicks from any other platform or software that you can think of. So we're going to start with something very simple, and then gradually we're going to talk about all the different pros and cons and improve upon the system until at the very end, we end up with a system like this. All right, so with that being said, let's talk about the simple system at first. So in this diagram over here, looking from left to right, you have the client to the left. The client is the user's mobile or their browser. Whenever they click on the website or on the ad, there is an API request coming to your backend endpoint. Let's call that API log_click. When your backend or your endpoint receives this request, it can go ahead and write the click event into a MySQL table. So the design over here is very simple. The whole flow is synchronous, so the client has to wait until the click has been stored successfully into the MySQL table. But this design should work for most of the small applications. But the big question is whether it's going to scale with your application as more and more users are coming to visit your website or application. So now let's run some numbers to see how on a larger scale the design is going to look like, and if this is going to scale or not. Let's say your app or your website is very popular and you're getting around 300 million daily active users. That's over here, right? And amongst these 300 million users, let's say each user has 10 meaningful clicks every day. By meaningful clicks, I mean clicks that you want to actually track, because most of the time, you don't want to track every single click happening in your application. So that's 300 million users with 10 clicks every day, which leads us to 3 billion clicks per day. Now, if we try to calculate the query per second, or QPS, that comes up to around 35,000 QPS. Of course, in your application, depending on what app it is, you are going to have peak traffic hours and hours in the day when the traffic is very low. So just as a rule of thumb, if you're looking to estimate the peak queries per second, you can just double your average QPS. So our QPS we found was 35,000. Doubling it would mean a peak QPS of 70,000. To calculate the storage, let's assume that one-click data, so this is all the data you're storing in the database for each click. Let's say that is 0.1 kilobyte. We have 3 billion clicks that we're recording in our database every single day. That means around 3 terabytes of data, of new data, is being added to the system every single day. Now, with such a high QPS and also with so much storage, this system that we designed is going to start running into many different issues. So let's start with the first issue and try to improve upon it. The first issue is with such a high QPS, especially during peak traffic hours, such a synchronous and blocking system can get very expensive and your server can become overloaded very, very quickly during the peak hours. So if you remember from the calculations we did above, the nature of the application is very high and spiky queries per second. That means the servers will need to be over provisioned so that when the peak hour comes, your server doesn't have to scale up very quickly. It can just be there ready to record all the clicks as the traffic is increasing. The main problem with this synchronous system is that given the whole thing relies on the API call between the client and the API server, this is more likely to run into many different errors. It can be just your server starting to run into different timeouts when the load is too much, or your server just crumbling down under the load. And because of that, you will be unable to record every single click happening in a period of time. So we need to make the system more scalable, elastic, and fault tolerant, right? So let's see how we can move away from this very synchronous and blocking system into a more decoupled and highly scalable one. Okay, so in this diagram, I am gonna zoom in a bit more. There you go. So this is the improvement upon the basic one we were talking about. So let me run you through what's happening here. So to make the system more asynchronous and non-blocking, what we're gonna do is instead of relying on the client to make a direct API call to our server, we are gonna use the log files that we have in our organization. Most of the clicks, it depends from application to application, but we're gonna make the assumption that most of the clicks in your platform is leading to one of your domain's URL. It can be either the final destination or it can be some kind of a redirect where before sending the user to wherever they clicked, you take them through a redirection. So your log file will be aware of that click happening on your website or platform. Okay, so we're gonna make the assumption that all the clicks are gonna be available in some kind of a log file in your system. So all the clicks are coming to the log file, and the log file you see is over here. The first thing we're gonna add is something called a log watcher. This can be just a very simple program which keeps an eye on the log file or log files in your system. And whenever there is a new log coming in, one log is one record of click happening, right? So whenever a new click comes in into the log file, the log watcher is going to read that new line and it's going to pass it along to Kafka, which is going to be the messaging bus that we're going to use in our system. Okay, so the watcher is reading any new logs that's coming along and then writing a message to Kafka with all the relevant details of that click. So the Kafka you see is over here. Now that in this system, we have clicks flowing into Kafka in almost real time, we can write a stream processor on top of that Kafka topic. What the stream processor is going to do is it's going to have some logic to consume from a particular Kafka topic and write that message into the MySQL table. So we are keeping the MySQL table as is for now, but instead of making this whole thing synchronous and blocking, we are making it more asynchronous by adding Kafka and ingesting the clicks from the log file as opposed to directly from the API call the client is making. Okay, so the stream processor is going to be more lightweight than a fully fledged API server over here, which is going to let you scale up and down very, very quickly. And the job of the stream processor is going to be very simple. It's just going to take in a record and then write it back to MySQL. And if you have to do some aggregation, that's when it gets a tad bit more complex, but we're going to come to that in like two or three sections. All right, so now that we have this system built, which is using Kafka, a stream processor, and our MySQL table, let's see that how this system will let you scale up and down much more quickly than this system was. Okay, so the first bottleneck you can think of is of course Kafka, because every single thing now is going through Kafka. So we should be able to scale our Kafka cluster, and the easiest way to do that is by adding more partitions, because your log watcher is going to write all the clicks into the same Kafka topic. And you can easily add more partitions to the Kafka topic so that your consumers can independently consume from the different partitions. So we will be able to scale Kafka just by adding newer partitions. The next thing you can think of is the stream processor. How do we scale that? So that shouldn't be a problem either. Now that the stream processor is a more lightweight and independent process compared to a whole microservice with API endpoint exposed, it's going to be much more easy to scale up or down the stream processor. So depending on the Kafka partitions, we can also scale our stream processor instances. So let's say you bump up your Kafka partition from 2 to 10. Now you have 10 partitions being written to. What you can do is also scale up your consumer, so scale up your stream processor from 2 to 10 instances. Now you have one instance of the stream processor listening from one partition of Kafka. So the whole system becomes more scalable compared to what we had before. And of course, if you're doing any aggregations in the stream processor, you might need to maintain some local state, which would mean the more data you consume, and depending on the logic inside that stream processor, your memory consumption might increase. So you should be able to bump up the memory of the stream processor instance. That would mean reprocessing some of the data, but the way most stream processors like Flink or Beam works, they will let you checkpoint your state so that when you bump memory and a new instance comes to life, it's gonna start processing from where the last instance stopped. Okay? So yeah, this is the more asynchronous system, and we just saw at 2 further scaling techniques we can use if your application is becoming more and more popular. Now, the second issue is related to storage. If you look at the diagram here, we are still using MySQL, but let's see, now that we did the calculations over here, let's see if MySQL is still a good choice, or is there something better that we can do? Okay, so we're gonna run through some of the application requirements once again to kind of like refresh your memory. The first thing is the application has high and spiky queries per second, depending on what time of the day it is. Given you are tracking clicks, the application needs to be very write intensive. If you recall from over here, we were getting around 3 billion clicks coming in every single day, which is around like 70,000 writes per second, because all your queries are writes. So you can interpret this as 70,000 writes per second. Okay. So yeah, it is very write intensive. When it comes to storage, every single day, we are adding around 3 terabytes of new data. Now, another key thing to note is, do we really care about storing every single individual click, or do we care more about the aggregations, right? In any kind of click tracking system, usually you care more about the aggregations than the individual clicks. Now, what do I mean by aggregation? What that means is, instead of reading every single click event, what we are more interested in is the aggregation of the clicks, such as how many clicks did a particular ad get in the last 90 days, or how many clicks did a particular YouTube video get in the last 48 hours, the last 24 hours, or the last 3 days, right? So aggregations is like summing up all your individual clicks over a particular time frame. But we still do want to keep the individual clicks for historical purposes, but we mostly care about writing and reading aggregations. Which brings us to the read pattern. As mentioned above, most of our reads, most of the requirements that we have when it comes to read is reading the aggregation of the clicks, such as total clicks in the last 20 minutes, total clicks in the last 30 days, or total clicks per advertisement in the last 90 days. Okay, So these are all the requirements that we have. And now we're gonna choose a storage or database depending on these requirements that we talked about. So based on that requirements, let's list a few of the issues that we can see with the MySQL database. Okay. The first issue is that the high write throughput might introduce too much latency in the system because of replication lag. If you remember replication lag in a relational database, usually you have a leader-follower architecture where all the writes go to the leader and asynchronously the leader replicates the new data into the follower or replica nodes through what we call like a replication system. If you're writing too quickly to the leader node, you can start running into a replication lag where your follower or your follower nodes don't have the most up-to-date data, hence introducing latency into the system. So we will need a database that can handle such a high volume of writes better than a MySQL or any other relational database. The next issue is that 3 terabyte of new data per day means that a lot of storage needs to be consumed every single day. And storing so much data in a relational table can get very expensive very quickly. The third issue is that we mainly care about aggregations, not the individual records. By records, I mean individual clicks, right? And relational databases won't do very well when you're running complex aggregation queries. It's perfectly fine for doing simple select queries, but when you already have like 3 terabyte of data coming into the relational table every single day, and on top of that, if you also want to perform some complex aggregation queries to get all your aggregation, it's going to start running into a lot of latency and your query speed is going to start suffering very quickly. So keeping all those 3 issues in mind, what I can think of is Cassandra as a better solution for our storage engine compared to a relational table like MySQL or Postgres. So in this diagram, you can see all we're doing is swapping out this MySQL table with a Cassandra table, right? And some of the features that makes Cassandra more suited for an application like this is it's very, very good at handling high write throughput. You can scale Cassandra databases very, very quickly because it horizontally scales. So we can store huge volumes of data more easily. In a relational table, scaling up or down gets very expensive because you can't horizontally do it. Most of the time, you would either have to vertically scale up your instance or you would have to shard the database into multiple different shards, which can also be a very expensive and time-consuming process. So Cassandra being able to horizontally scale makes it a much better candidate to handle an application which is going to get such a high throughput of writes coming in. And if you remember from the aggregations we were talking about, all these aggregations are time-based, so total clicks in X minutes or 30 days or 90 days. And Cassandra is very good for storing time series data, and you can retrieve time series data very quickly from Cassandra as opposed to doing complex queries in your relational database. All right, so now that we chose Cassandra, let's talk a bit about the data model and how or what kind of data do you actually want to store in the database. Okay. So the 2 questions that comes to mind is where do we store individual clicks and where do we store the aggregations, right? If you remember, we mainly care about aggregations over here, but we also want to keep the individual clicks for historical purposes or just for data integrity purposes, so that if for whatever reason your aggregations are wrong, you can go back and reconstruct the aggregations from the individual clicks that you're storing. Okay. All right, so for the aggregation data, as you can see, we have to access them more frequently. Imagine a bunch of dashboards that different companies are using to perform how their advertisements are doing. And as a result, whenever someone looks at this dashboard, we would need to run these aggregation queries because the campaign managers or whoever is analyzing all these data, they don't really care much about individual clicks. They mostly care about the trends and how the clicks are increasing or decreasing over time. And of course, the aggregation data will need to support multiple different time slices. As you saw over here, we might be interested in 20 minutes, 30 days, 90 days, or maybe 2 years, 3 years, something like that, right? For the individual clicks on the other side, they will be rarely accessed because, as I mentioned, we mostly care about aggregation, but we still do want to keep them for historical, backfill, or backup purposes for the future. So we still want to store them, but we can make the trade-off where even though we're storing them, we don't necessarily have to access them very, very quickly every single day, like we will have to for the aggregation data. Okay. So that means what we can do is we're okay not storing the individual clicks on Cassandra because we know that we don't have to retrieve the individual clicks every single time. So we can have a system like this where the log watcher, once it messages the click to Kafka, one system, which is also a stream processor, is passing those individual clicks into a cold storage like S3. What a cold storage does is it gives you lots of storage for very, very cheap. So you can store huge amounts of data, but for very cheap. The only trade-off you're making is it's not going to be very easy to read the data whenever you have to. Given one of our requirements is that individual clicks does not need to be accessed very frequently, and we're only keeping it for historical purposes, we are okay making the trade-off where we keep the individual clicks in some cold storage system, such as AWS S3. And then we have our other pipeline, which we already had, the stream processor, that's going to actually do some joins and do some stream processing, find the aggregates, and store the aggregates into Cassandra. So now Cassandra won't have too many data that we don't need to query. And the data models in Cassandra can also be designed to exactly fit the kind of aggregation queries that you're expecting. And all your individual clicks are ending up in the S3 cold storage. So yeah, just to repeat, why use S3 for individual clicks? It is cheaper to store, and we don't really need to access the data often, which makes it a perfect candidate for data such as these. Now, how do we store the aggregations in our Cassandra table? You will have to design your Cassandra tables, keeping your queries in mind. So if you have queries mostly getting data for the last 90 days, 30 days, 20 days, or if your queries are more based on shorter time frames, like maybe you want to query for clicks in the last 20 minutes, 30 minutes. So depending on what kind of time slices that you're interested in, you want to design your Cassandra tables according to that, which means you will have a bunch of redundant data because you might store the same rollups or the same aggregations in different tables based on different time slices, right? To give you an example, you might have one Cassandra table that's storing your click aggregations by the advertisement ID all time, right? So you have the primary key or the partition key as the advertisement ID, and then your count is the total number of clicks that the advertisement got over time historically. And then you can have another table that has your clicks, so like your ad clicks by the month of the year, right? So you can see how many clicks did this advertisement get in the past 90 days or the past 30 days, something like that, where given you have the data by month, you should be able to easily access it. And then you can have another table with the same data, but instead of breaking it down by month, you break it down by hour, or you break it down by minutes. So you can see that in Cassandra, to get the best performance, you are going to have some redundancy, but as long as you design your Cassandra tables according to the kind of read queries that you're expecting, it's totally okay to have some redundancy to get better performance. All right, so that's everything about storage. So now we ended up with our primary database being Cassandra, where we are storing all the aggregations. And then we have a cold storage of S3, where we're storing all the historical individual click events. All right, so now the next issue is going to be data inconsistency. If you take a look at this diagram over here, we are doing all the aggregations on a stream processor. So the stream processor is acting on the Kafka stream in real time. So as data is flowing in, the stream processor is keeping them in memory, counting them up, summing them up, and then outputting the message to Cassandra. So given the entire thing is happening in real time, there can be some inconsistency when it comes to your aggregate, right? So let's say that your stream processor found 20 clicks that happened in the past 1 hour, but in like actually what happened is it wasn't 20 clicks, it was like 25 or 30, something like that, right? So you should accept the fact that your stream processor is not going to be 100% accurate. And the main reason for that is something called late data. I am going to have another video that talks about stream processing and the concept of late data and how you can handle late data. But the idea is that in the stream processor, let's say if you are aggregating all the clicks for a given advertisement every 2 minutes, right? So your stream processor job, every 2 minutes, it's going to sum up all the clicks for a given ad ID and write that to the Cassandra table. Now, what happens if, for whatever reason, an event that happened in that 2-minute window comes into your system later than that 2 minutes, right? So let's say we're talking about a window from 3 p.m. to 3:02 p.m., right? Your stream processor is going to wait from 3 p.m. to 3:02 p.m., sum up all the events, and then at 3:02 p.m., it's going to write that aggregation into Cassandra. Now, if a late data comes after 3:02, your stream processor is not going to process that data because it has already written the aggregation of that 2-minute window into Cassandra. So you're going to end up not counting this in your aggregate. So you can see by that example how aggregations in real time can be slightly inaccurate, and we need a way to fix it, right? Maybe if your application does not care about 100% accuracy, it's totally fine to just ignore it. But more often than not, you will need the exact number, especially when it comes to things like ad clicks, right? So we need a system to make sure that the data in Cassandra somehow reflects the exact number, not just an approximate one. So when it comes to fixing it, we are going to have a very simple solution. So you see we already had the whole system here. All we are adding is the Kafka batch job and the lines over here. Now let's talk about it, right? What we can do is we can have a scheduled batch. This is going to be maybe a nightly batch that runs once every night, or maybe even a batch that runs once every couple of days. What the batch is going to do is it's going to read the cold storage, or S3, to get all the historical clicks, so all the individual clicks that happened in the past day. It's going to feed it back to Kafka, run it through the stream processor again, and the stream processor can go ahead and update Cassandra with the aggregations. What this means is you don't have to worry about the inconsistencies that happened in the first pipeline, because that is real-time data coming in, which you don't have much control over. In this pipeline of the batch job, all the clicks are going to be there in the cold storage for sure. Because this stream processor job, it does not care about late data. All it cares about is whatever data I'm given, I'm going to just write them to S3. Okay? So the batch job, when it reads from the cold storage, 100% sure it has all the clicks that your system ever received. So the batch job can go ahead and read those, republish the message to Kafka, and then the stream processor can go ahead and update the aggregations for that day's data. Okay, so I have the steps over here. Your scheduled batch job, it reads the individual clicks from S3 over here. It republishes them to another Kafka topic, the one you see over here. And then the stream processor, it goes through the Kafka messages without late data, because we know that all the clicks are being accounted for now. And it goes ahead and updates the aggregation in the Cassandra table. Alternatively, if you don't want to deal with another Kafka pipeline, you can make the batch job directly calculate the aggregations and directly write them to Cassandra instead of going through the stream processor again. That's also possible, but that means your batch job will have a lot of duplicate logic coming from your stream processor. Okay. So yeah, now we have a way both to aggregate counts in real time and an offline process that corrects the count or slightly tweaks the count every night or every couple of days. Okay. That means in this system, you should be able to get the aggregation of the clicks in real time, but it might not be 100% accurate. But at the end of every single day, this batch job should correct those slight inaccuracies. So even though over the course of a day, your data might be slightly off, at the end of every single day, historical data up till that day should be corrected every night. So you should be good on that. So yeah, that's the system that should let you track any kind of clicks coming into your system in real time. It can be advertisement clicks, YouTube video clicks, or just clicks on your own website or application. So hopefully that was helpful. I am going to have a different video on stream processing and the different kind of window operations you can do on a stream processor. Expect to see that maybe like a few weeks from now, once I'm done with the system design videos. With that being said, I hope this was helpful. If you have any questions, just leave them in the comments below and I'll try to get back to you as soon as I can. And yeah, have a good rest of the day. Bye-bye.